Okay.
Okay, good Friday morning, Backyard Naturalist. It's so great to say those words again after being away for a month as we kick off a brand new season, season 4 of the Backyard Naturalist. I often reflect the pandemic has done a lot to this world. It's done a lot to us. It's brought a lot of trauma. It's brought a lot of chaos. It's affected a lot of changes, but there were some lemonade stands that came out of those lemons, and one of the best pieces of lemonade, if you can have a piece of lemonade, that arose for me was that the time I get to spend with you all every Friday morning, reconnecting with old friends and making new ones as we explore the green spaces nearest and dearest to us, our backyards. And we had no idea how long this little experiment, this reaction to stay-at-home orders would last. And we still don't know how long it'll last, but the UEC's research team has committed to at least one more year of these Friday mornings together, and that makes me happy as I've come to know and appreciate some new friends who share a passion of learning and exploring with me. This season will continue to bring you great topics mixed with a lot of fantastic guest hosts from around the area, around the state, around the region. And so thank you for joining us this morning, whether you're here live or watching recorded. I'm honored to be spending this time with you. And we're kicking off the season with a big topic, with a huge topic, a huge hot topic. I'm not sure if there's an object in the universe, and this isn't hyperbole, that has a greater effect on our backyards than the sun. Maybe the soil, maybe the weather, but none of those would be what they are without the sun. So we're kicking off the year in a big way. I feel pretty underqualified to try to tell the stories of such a massive force. Our sun can tear down and destroy with fury. It can kill, but it can also gently coax a delicate dragonfly from its slumber with a gentle morning kiss. So I hope you're comfortable, and I hope you're ready for some stories about our own neighborhood star, the one we call the sun, in episode 1 of season 4 of the Backyard Naturalist, the Prodigal Son. But first, I'd like to give a warm, heartfelt thank you to the many subscribers we've had over the first 3 seasons. You're the reason we're still here. You're the reason we're taking this leap of faith into season 4. Some of you were with us back in April of 2020 when the very first episode, Desperate House Sparrows, debuted. And I hope if you're listening, you consider supporting the series with a subscription. New for season 4 is that we're going to have a series of monthly in-person, not behind a screen outings to explore some local areas around the greater Milwaukee area. So I'd love it if you joined as a subscriber, but whether you do or not, whether you can or cannot, I'm glad you're here. The featured star of today's episode is 93 million miles away, give or take, from our backyard. But because our backyards don't have a ceiling, they don't have a roof, they're not enclosed in a bubble, the backyards give us a view into the heavens. And even though the series kicked off with mostly critters, with wildlife, animals and plants, the birds, the insects, the trees that we find in our backyards, objects in the sky, astronomical processes are every bit a part of our backyard as that monarch butterfly, whether they affect us directly like the sun, or if they just give us cool things to look at. We as humans tend to and have tended to be fascinated with the stuff that goes on in the sky. And so you may have heard the recent news about the Artemis mission, which has a goal of getting people, humans, back under the surface of the moon for the first time since the Apollo missions. So the Artemis 1, the first mission, will not be carrying humans, but it'll be carrying 3 human mannequins that will are going to be outfitted to measure and study the effects of the mission on the future real-life humans. And the 3 mannequins will be joined by, and I'm not making this up, a Shaun the Sheep doll. So the mission was set to go off on Monday, but there were some engine issues, and it's cool. It's not, you hear like, oh yeah, Delta canceled this flight due to technical issues. And you hear, okay, there are engine issues on this flight. But then it's kind of cool once you look into, well, what are the engine issues? So again, it was set to go off Monday. Once it's launched, so the mission itself, once it's launched, a space capsule is going to be carried by this massive rocket into orbit around the moon, and then it's going to return to the Earth, hopefully. Then the first launch, they had to cancel. The second launch is, I think, supposed to happen tomorrow at 1:17 Central if the weather permits. But the reason they couldn't launch on Monday is that in order to get this rocket up to work well, there's 4 engines, and each of those engines need to be cooled to minus 420 degrees Fahrenheit, so that when the propellants come through them, the propellants are super, super cold. If they weren't cooled ahead of time, those propellants would shock the system, and the metals might crack from being cooled so quickly. So they have to bring the engines down to that temperature, so using liquid hydrogen, so that when the propellants go through, it doesn't crack the metal. So the liquid hydrogen cooling line on one of the rockets wasn't able to get that particular rocket as cold as it needed to be. So 3 of the rockets were at minus 420, but one only made it to about minus 380. And, you know, to me, that doesn't seem like a big deal, but that was enough to temporarily scrap the launch. So now after reviewing and after looking at it, they think that the engine was actually cold enough to launch, but they think it was a faulty sensor. So they're going to try again. And even if that sensor reads 380, if everything else, you know, is to what it's supposed to be, they're going to probably try to launch. But if they can't launch by early next week, they have to take the whole rocket back to the vehicle assembly building. And the reason they have to do that is that there's a system on board that would, if for some reason the launch happens and the rocket goes off course and starts careening towards Earth, which could be a problem, there's a system that'll explode the rocket before it hits the Earth. So kind of preventing us from getting destroyed by the rocket. So if they can't get it launched by early next week, they have to retest that system to make sure that works. And to do that, they have to move the rocket back into the big system. So it just amazes me, all of the tiny, tiny, tiny details and all of the systems that have to happen to make this go. It's just why it costs so much money, why it takes so long. But it really is an engineering marvel, for sure, that we did, 40 years ago. So 50 years ago, 60, long time ago. So, and then before we go back to space for our featured star, we in our little talk beforehand, Eric reminded us that he had seen like 350 or 360 common nighthawks migrating in a parking lot in Milwaukee here, and this is a really fun time of year for migration, and this is the time of year when we tend to notice 2 very different flying organisms congregating in very large numbers right about the same time of the year. So you have the big darner dragonflies that amass in huge numbers. We've had people said they've seen millions of them, and then hundreds or maybe even 1,000 of these birds at the same time. Undoubtedly, some of these dragonflies are probably making a nice meal for the nighthawks. But this is a great time of year to explore not only your backyard but your neighborhood. As dusk approaches, we're getting towards the end of it, but they're still here. As dusk approaches, maybe an hour before sunset, chances are good that you'll find one of these 2 groups en masse. For the dragonflies, you want to look over fields, and then really there's not much of a rhyme or reason, I think, where the nighthawks are. It's kind of a matter of luck, but all the more reason to get out and walk and explore your neighborhood collection of yards and wildlife. And finally, a quick shout out. I used several reference sources for the stories I'm about to tell, but the bulk of it comes from the How Stuff Works conglomerate, a very worthy and fun one if you haven't checked them out, and the podcast Stuff You Should Know. Okay. Our sun, the one and only sun. Some might say, well, it's just a star, a pretty average star at that. Our sun is only slightly above the average size of all the other stars out there, and there are a lot of stars. We estimate that the universe holds 200 billion trillion stars, But of all those 200 billion trillion stars, only one of them is the sun, is our sun. And so, like many of these featured backyard naturalist stars, there were many, many different directions that you could take an episode about the sun. So it could be a mini series or a macro series. There's so much about the folklore, the mythology, astrology, astrophysics. But my goal today was really to just try to strip it down to the most basic level, the most basic question: what is the sun? What is the sun? How does it work? We know that we rely on it. We know it can be beautiful and destructive. We know it's powerful. And at least so far for humanity, it's been everlasting. But what is it? So again, the most basic level, it's a huge ball of gas. It's not on fire. There's no combustion happening. It's a very reactive, very large ball of very hot gases. And believe me, I'm familiar with gas, probably too familiar with gas if you ask my family. And the gases that I'm used to don't form this nice round sphere in the living room. Like the sun is this nice round sphere. So maybe it's best to say that the sun is a lot of gas, an enormous amount of gas, so much gas that its mass collapses under its own extreme gravitational pull. And then all that mass creates this nice round sphere. And it's so much gas that its movement, internal movement, creates its own magnetic fields. So a lot of gas. I think we probably could agree that it's good that there's a lot of gas because our existence relies on there being a lot of gas in the sun. So not only for the life-giving properties, but also because that mass of gas keeps our Earth and the other planets and all the asteroids and all the comets in our solar system together. So thank you. It's a good thing our sun has all that gas, all that mass, and all that gravity. This massive ball of gas, if I haven't said that yet, has a radius of 432,000 miles. That's 109 times the radius of the Earth, so a little more than 100 times the radius of our Earth. If you've ever hung out with my dad, Victor Vargo, the conversation probably doesn't go very far before he starts asking you the question, so if the Earth were the size of a pea, how big would the sun be? And how far away would it be? And how big would the nearest star be? And all that. So the size and distance relationships of our solar system are pretty massive, which is why most models of the solar system that are to scale and effective are best put along like hiking paths or biking paths, I know, a mile long because the distances are so great. So if you ever have some time to kill, it's fun to just, Google if the Earth were the size of a pea or the size of a basketball or an atom. And here I found just a kind of fun basic comparison of the Earth, the sun, and the moon.
Have you ever wondered about the scale of the solar system? So imagine this soccer ball, the football here, represents the Earth. How big would the moon be on this scale? About as big as this tennis ball. So the moon is about a quarter of the diameter of the Earth. And how far apart would they be? About that far. And how big would the sun be on this scale? Approximately twice the size of the houses in the background over there. It wouldn't be able to fit in the gap between the Earth and the moon. In fact, it's over 3.5 times larger than that. And on this scale, it would be approximately 2.4 kilometers, or about 1.5 miles away. The sun is pretty big.
So we classify stars in the universe mainly by size, the size of the star, the temperature, and then the wavelengths of light that they emit. So our sun, if you're keeping track, is classified as a G2 star, also known as a yellow dwarf. And it's also a population 1 star, which means it's one of the younger stars. And the younger stars tend to be more heavy element rich. There's also population 2 stars that tend to be older and heavy element poor. And then astronomers think that there's a population 3 classification of stars that are so old that none of them are around anymore. So we're pretty sure that the sun was formed about 4.5 billion years ago, and that there's enough fuel in the star for it to continue to emit light for another 5 billion years. So that's good for us, good for the many generations to come, depending on how long humanity can make. And then just a few kind of fun, quick trivia points. So the sun is about 93 million miles away, it give or take, depending on the time of year. And that's about 8 light minutes, or the distance that it takes light to travel in 8 minutes. So we measure the distance of other stars in our galaxy in light years, not light minutes, because they're really, really far away. And then another thing that is really, really far away is the center of the Milky Way galaxy around which our sun revolves. So the sun is 25,000 light years away from the center of the galaxy. And it takes 250 million years for the sun to make 1 trip around the galaxy. So we, as humans, sometimes measure our birthdays as the trips that we take around the sun. And then I did the math. If we did the same for the sun, if the sun's year is equivalent to 250 million Earth years, and the sun is 4.5 billion years old, if my calculations are correct, that means the sun has gone around the galaxy about 18 times. So happy 18th birthday to our beloved sun. You can get a tattoo now and vote. I forget what else you can do at 18. There are just a ton of fun facts about the sun that we could continue, but I think that's, kind of kicking the can down the road of understanding what the sun is. And so we'll look at the sun starting with the different parts of the sun. And I kind of brought a naivete with me. I think I've carried it with me. I never really think of the sun as being that complex. I think of it as being super important, super powerful. But I don't think of the sun in that filter isn't there, that I think of it as really complex. But I think, as this diagram shows, you can see how wrong my base opinion is, and how long maybe it's been since I studied the physical sciences in school. So yes, the sun, in addition to being massively powerful, is pretty complex. At its core, the process is really simple. So we're starting with the core, the center of the sun, not only because it's the center physically, but kind of metaphorically. It's the key to understanding what the sun is. And again, at the most basic level, it's pretty simple. So the core is extremely dense. It only makes up 2% of the volume of the sun, but it's also half of the density of the sun. So very compact, very dense. And it extends to about 25% of the sun's radius. So because it's so dense, there's an extremely intense gravitational pull. And this is the key to the sun as the giver of light, because that core is a nuclear reactor, and it's a fusion reactor. So what that means is that the gravitation is so intense, that pull is so strong, that all of the hydrogen atoms that are just kind of hanging out there become squashed together so tight that their nuclei fuse together and join to become a new nucleus, which becomes a new element, helium-4. So when we say the sun is a nuclear reactor and a fusion reactor, it's because the nuclei are fusing together to form new elements. But the most important part of this reaction is that the end product, the helium, has less mass than the 2 hydrogen atoms that are combining. And because matter and energy cannot be created nor destroyed, that extra mass that doesn't make it into that final helium atom becomes released as energy. as electromagnetic energy throughout the spectrum. So gamma rays, X-rays, those skin damaging UV rays, life-giving heat rays, rays in the visible spectrum that allows us to see. And that is all packaged as photons. So that's all of that electromagnetic energy is traveling as photons, and that's really it. So in the core of the sun, hydrogen atoms are fusing together to create helium, and in the process, energy is released, which is why the sun is so hot and bright. So that's kind of the core of understanding it, and astrophysicists try to understand it at a much deeper level, but for me, that's good enough. And I think that's the most important part of the story. And to look at it another way, you have gravity pressing inwards, and this causes, again, the hydrogen atoms to squash together and form helium. And then that extra energy that's released needs to go somewhere. And so that energy in the form of photons begins to radiate outwards, counteracting the inward pull of gravity. So you have all these photons being produced, and then now they have to go somewhere. They're ready to travel. They're ready to come, warm you on Earth, but it's not a straightforward path from that core to you. It's actually way more complex. So you have, again, gravity pushing in, the photons are going out, but right after that photon is produced and it's ready to make that journey, it leaves the core and enters what's called the radiative zone. So that's that middle layer. It extends a further 55%, 45% of the sun's radius. And then, so the photons from the core hit that radiative zone on their way out. They're ready to go through space, but then immediately they realize that their journey is going to be a very short one. The average photon travels a micron, which is a millionth of a meter, before it gets absorbed by one of the gas molecules in the radiative zone. So a photon is born, it's ready for this long journey from the core, and then immediately after the tiniest journey, it's absorbed by another gas molecule. That's it. But that's not the end of the journey, because as soon as it's absorbed by that other molecule, it heats that molecule up and causes that molecule to release another photon of the exact same wavelength as the incoming photon. So the photon comes in to the gas molecule, and then another one comes out. And then that outgoing photon also travels just a micron before it hits another gas molecule. And so that entire process for that photon to travel through the radiative zone takes 1 million years. 1 million years to just make its way through that one zone. And during its journey through that radiative zone, that process of being absorbed and re-emitted happens 10 to the 25 times, 10 to the 25 power. So that's what the number 10 to the 25 looks like. That's how many times a single photon gets absorbed and re-emitted in its simple journey from the core through the radiative zone. It's not an exact analogy, but just pretend you're trying to get across a football field. And every step you take in that football field, there's a little portal that pulls you in and spits you out in a new random direction. So progress becomes extremely slow. And because the football field is 400,000 miles long, no matter how fast you are, and photons are as fast as you can go, it's going to take you a long time to get across that football field, right? Because you're like that on the upper right shows you the average, path of that photon. It's not a straight line out. It hangs out there. It lives in that place for a long time. So then you have the core the photons are being emitted from. You have the radiative zone. The photons are in that endless journey to get through. And then the next layer of the sun is called the convective zone. That's the outer layer. And that makes up the last 30% of the sun's radius. So the photon finally breaks through the radiative zone and it gets to the convective zone, only to face the harsh realization that it now has to take another 200,000 years to make it through that next layer, 1 to 200,000 years. So, from the perspective of that brand new photon, it's born, yay, here I come. Then it takes 1 million years just to get through one zone, then another 200,000 years to get through the next zone. But then when it escapes from that zone, it only takes 8 minutes to get to Earth. So it takes 1.2 million years to travel the 400,000 miles through the sun. And then once it escapes the sun, it only takes 8 minutes to travel the 93 million miles to you. And on the flip side of that coin, think about this. So the next time you're out feeling the warmth of the sun on your face, that morning sun, those rays, those cozy photons that are hitting your face, it feels so comfortable, makes you smile. Those photons were created 1.2 million years ago, which to me is just super cool. You're feeling energy that's over 1 million years old. And really your skin is just part of that journey, because your skin molecules are absorbing those photons too, and then re-emitting them as heat, which is just another way station on this photon's continued journey. But again, it just blows my mind in a good way that when you're basking in the morning sun, you're feeling photons that were created over 1 million years ago in the core of the sun. So back to the 3 main layers of the sun. One more quick thing about that convective zone that you can kind of see in this diagram. It's called the convective zone because it's a very dynamic layer characterized by convection cells, these rising and cooling gases. And to quickly borrow a slide from the talk on wind from a few weeks back, convection cells are these loops of hot material rising and then cooling and sinking in a cycle. So just like when water boils on your stovetop, or whether it's magma in the earth or air in our atmosphere, those are convection cells. And that happens in the sun in the convective zone. So that's areas where super hot gas rising and slightly cooler gas is sinking. And it's this movement of the superheated gas. And when gas is superheated, it becomes plasma, the 4th element after liquid, solid, and gas. And because it's plasma, the movement of plasma creates a magnetism. And that becomes super, super important to the story. So 3 layers of the sun, just like the Earth. The Earth has a core, a mantle, and a crust. The sun has a core, the radiative zone, and the convective zone. And then also like the Earth, the sun has an atmosphere above the surface. And the atmosphere also has 3 layers that we've identified. So in the center of the diagram here, you have the layers of the sun in the middle. And then the atmosphere above the sun's surface is also broken into 3 layers. So you have the photosphere, the chromosphere, and the corona. So starting with the innermost layer of the photosphere, it's only about 200 miles wide. It averages 5,800 degrees Kelvin. And if you're like me, I have nothing to compare what 5,800 degrees Kelvin. I just know that it's really hot. So the outside edge of the photosphere, you can see it's that kind of nice white thin line in the middle there. That's what gives the sun, our sun, this clean, crisp, round edge. Because think of, there's a lot of massive power happening there. So that doesn't, lean itself to this nice edge, but because of this layer, this kind of cooling layer, that's what gives the sun that really round edge. But please don't try to look for that edge with your naked eye. As important and life-giving as the sun is, it can also destroy the cells in your eyes if you look at it. So never look directly at the sun. You can look at pictures. You can look through specialized glasses or filters on telescopes, and that's okay, but never look directly at the sun. Oops. The next layer after the photosphere is the chromosphere. And that's normally about 1,000 degrees Kelvin cooler than the photosphere on average. But unlike that crisp edge of the photosphere, the chromosphere has its own convection cells. So it's a lot more dynamic. It doesn't have that nice edge. And so you see all those little purplish tower fingers kind of poking up. Those represent the convection cells. And so even though on average it's cooler, some of those convection cells can reach 10,000 degrees Kelvin, which is really, really hot. And then that extends another 1,200 miles above the photosphere. And then we come to everyone's favorite layer, the one so important we named a beer after it and a pandemic causing virus after it, the corona layer. And the corona can extend way beyond the surface of the sun by several million miles. And the corona, for whatever reason, takes the level of hot in the sun to a whole new level at about 2 million degrees Kelvin. And we've known about the corona layer for a long time, probably way longer than any of this other stuff, because it has revealed itself to humanity over and over again during solar eclipses. So when you see that striking edge of the coronal layer beyond the edge of the eclipse. And interestingly, even though we've known about the coronal layer for a long time, it's still one of the least understood layers of the sun. Why does it get so much hotter than the surface of the sun? It's something that all the smart people that are studying the sun still don't understand. So if they don't understand it, I'm good not knowing the reasons other than the corona is very pretty and very hot. So those are all the layers of the sun. You have the 3 inside layers and then the 3 atmospheric layers. And that's a decent understanding of the structure of the sun. But then there's one more really important process to bring up that complicates things, but is super important, and that's sunspots. So again, you have the basic processes occurring, gravity pushing inward, energy being released outwards. But the key is that is not a uniform process. It's not a regular pattern that's happening. You have all these convection cells, and the sun is rotating around its axis, just like the Earth. So being a ball of gas, the speed of rotation of the gas isn't going to be evenly distributed. Gas at the equator takes about 25 days to go around. The gas in higher latitudes can take a few more days. It's slower. And then if you add to this, the kind of details of the convection going on in the chromosphere, it really adds a lot of layers of complexity and makes it pretty much a much more chaotic and unpredictable system, because you have movement north, south, east, west, up and down. So you don't have these regular patterns. It's much more chaotic. So you have a star that's not only releasing a lot of energy all the time, but it's not releasing that energy the same day to day or across the star. Some of that energy is being released in these fits and spurts, like a boiling pot of soup. And the energy is responding to that magnetic field. So all of this chaos leads to things like sunspots and coronal mass ejections. So it all starts with sunspots. So sunspots are areas of magnetic activity in the photosphere. And just like any good bar magnet, there are always 2 sunspots. Almost always, there's 2 sunspots representing the magnetic north and the magnetic south. So sunspots always come in pairs. And that then leads to a process called a solar prominence. So that's an arc of particles and radiation that can extend hundreds of miles out into the atmosphere in a similar way that electricity arcs between 2 poles. But they're characterized by entering and exiting at one of those sunspots. So a really cool process that happens because of the sunspots is this energy released in these arcs, but then that can boil over and erupt into what are called coronal mass ejections. So a coronal mass ejection happens when a magnetic field just bursts through the surface of the sun, and it releases a huge amount of plasma and magnetism from the corona out into space, and it travels through space, not at the speed of light. It travels through the space very quickly, but it can take a long time to reach Earth. So in this drawing, in the sun, you can see that there's that little arc on the top, and that's the solar prominence. And then just below that, you see one that turned into a coronal mass ejection underneath it. They're often accompanied by what are called solar flares, which are made up of light. And then here's where I need to turn it over to the folks at NASA to do a better job explaining the differences between a coronal mass ejection and a solar flare. But even if you don't understand it, this video is going to have some really cool images. Could watch that one a lot. So I know it's not the best comparison, but it is. I mean, to me, it's like watching a bowl of thick soup boil, and you have these little explosions every once in a while. But the solar flares leave as light, and then the mass ejections are actually the material, the plasma and the magnetic fields traveling together. So sunspot activity is cyclical. It's roughly a 22-year cycle from peak to peak. So 11 years between a peak and a trough, and then another 11 years to the next peak. We are just coming out of one of the low points. So it means over the next 10 years or so, we're expecting some increased solar activity. And peak solar activity, which is caused by, so peak activity is caused by an increased number of sunspots. So when there's more sunspots, that leads to a higher number of those solar prominences, and that leads to a higher number of these coronal mass ejections and flares. And so during the peak activity, the Earth, can become inundated with this radiation and these radioactive particles from the coronal mass ejections. And the downside of that is it messes with our magnetic fields, and those ionized particles can actually disrupt our electrical activity. It can cause blackouts. It can cause other problems. But then on the positive side, that increased solar activity gives us the beautiful auroras that you can enjoy, particularly if you're closer to the poles, the aurora borealis in the north and the aurora australis in the south. And then we'll kind of finish with just a few final questions. So first of all, what is the color of the sun? I think you give me a crayon, I'll draw the sun as yellow. But the sun is actually white, if you look at a picture of the sun, you're going to see it's orange, but the sunlight that hits the Earth is white because it contains all the electromagnetic radiation. And if you put all the colors together, the visible spectrum, that becomes the color white. So we tend to draw the sun as yellow for other reasons artistically, but the sun is white, and white becomes all the colors, or is made up of all the colors. And then every once in a while, a rainbow likes to remind us that the sunlight has all the colors available. We just need to tease them out. And then we see the sun as yellow or orange, particularly when we notice it in sunrises and sunsets, because then the light has to travel through more of our atmosphere to reach our eyes. The blue light is scattered first, which is why our sky appears to be blue. And then if more of that blue light is scattered, then only the yellows and oranges are going to make their way through to our eyes. And that's why we tend to see sunsets and sunrises with that yellow and orange color. Another really fascinating thing about the sun is that, it radiates all of that light, the gamma rays, the X-rays, the UV rays, heat, infrared, and it's also radiating sound. The sun makes sound. It's constantly vibrating. It produces a sound with 10 million individual tones at the same time. But we can't hear it because it's an extremely low frequency. So the lowest sound a human ear can hear is when the wavelength, the distance between the wavelengths is about a 20th of a second apart from when it hits our ears. That's about the lowest that we can hear. But the wavelengths of the sun's sound are coming at 2-minute long peaks, so really, really long. We can't hear it, and that's probably, I think, a good thing, because if we heard the sun 24 hours a day, that might be a little discombobulating. And then the final question we'll end with is so what's going to happen to our sun, right? In our lifetime, probably nothing. It's such a blip. But the sun has about 5 billion years of energy left to keep doing what it's doing. But eventually, the sun will turn into what's called a red giant. And when that happens, we won't have to worry, because the Earth will essentially become vaporized. So see you later, Earth. And then eventually, the sun will turn into a white dwarf. And then from there, a black dwarf. And we'll go out silently into the night as a lump of mostly inert carbon, as it turns out the light for the last time, which will be the end of a beautiful story, a story that allowed life as we know it on Earth to appear and flourish. But from stardust it came, and to stardust it will go. So thank you for joining me on this story journey. I look forward to seeing you next week and every Friday morning during season 4 of the Backyard Naturalist. I will stop sharing my screen.